As we move on to quantifiers and equality, it's important that you have a firm grasp of the first classical and non-classical sections, because most things in Lean are defined with functions. So unless you understand how to prove implications using lambdas, you will have a very hard time proving things like forall, because forall is basically a function. And I'm also going to take a moment to prove something similar to last proof, but instead of an if and only if, we're going to use equality. And you'll see how it can be a little bit different proving an equality versus an if and only if. So the book starts with the universal quantifier. I'm going to go ahead and start with equality. So there are kind of two ways of showing equality. One is by actually computing something. So in this case, for example, 2 plus 3 equals 5. Refl is reflexivity, right? So refl in Lean is not exactly just stating something is, proving something is equal by reflexivity. It's also applying any sort of computation that Lean knows is possible, such as addition, to prove the goal. That means that 2 plus 3, we can ask Lean to compute the sum to prove this, right? That's important to understand, because sometimes you just can't get around proving, equality by actually calculating. Whereas up until now, we've proven theorems, from building blocks of other theorems. We haven't ever needed to use computation. Computation is also very closely related to decide, and we'll get into that more in future episodes. For now, I'm just going to do a few quick proofs to demonstrate and solidify your understanding of certain tactics like substitute and rewrite, because they are pretty important once we start getting into more complicated propositions where you almost always are going to have an equal somewhere in there. So to prove that the transitivity of equality, we can use substitute, the subs tactic, to replace whatever we give it. So h1 in this case is going to be p equals q. By the way, you can type h1 with the cute one with \1. And we're going to substitute's going to take that and replace this wherever it can. So it will replace this in the h2 it will replace q with p. So after that, we're going to have h2 as being p equals r instead of q equals r. Now we could finish the goal directly like I do in this example here, because we have our assumption now matching the goal. We have h2 is now p equals r, and that matches our goal. So we could finish that directly. Or we could substitute again. We could substitute h2 in the goal to replace r with p to get p equals p, which of course can be solved with true reflexivity, no computation necessary. What about this one? Well, this one is the same thing, but using the rewrite tactic. Rewrite is maybe a little bit more powerful than substitute. It does a little bit different. It's not really replacing our hypotheses like substitute was. If you notice, after we do one substitution, it's going to actually substitute. It's going to take that hypothesis and consume it. Rewrite's just going to replace whatever it sees in an equality wherever it can in the goal. And you can give it, of course, we could give, if we wanted to model this behavior with rewrite, we could do rewrite h1 at h2 to get the new h2 as being q equals r. Now it did it in the opposite direction that substitute did, so we'll give it arrow to do the opposite direction. Now we have p equals r, and then we can do another rewrite at the goal, which we can actually define. I just learned this. You can give the turnstile and it should work. I guess it doesn't work with rewrite. Never mind. But if you leave that out, it's implied that you're going to be rewriting at the goal. We're going to rewrite the new h2 at the goal, and that closes the goal, because rewrite probably is doing a call to refl at the end. Yeah, refl afterwards. So we don't need this. That's basic propositions about equality. We're going to revisit the proof that we had last time, where we had not p if and only if not p, but this time we're going to prove it with equality. So we're going to show that it's still a contradiction if you use equality. Now, equal provides, let's take a look here. Equal has a method called I believe it's called toIf. Yeah, toIf. And toIf is going to take an equality and convert it to an if and only if. So of course we could, as our first step, we could rewrite eq to if inside the goal, and we could just use the existing proof. But I'm going to show you, for the sake of learning, how to prove an equality that's not trivial. We're going to use the same kind of proof structure that we had, but instead of what we did with like lambdas and function application, we're going to use a lot more rewrite, right? We're going to rewrite because now that we have an equality, rewrite is really good at solving these. So when we are here, we have an equality hn, p equals not p, that we assumed by contradiction, right? That was our initial hypothesis. And we have to show false. So what we can do is, the strategy is going to be basically, we're going to use our contradiction equality, and we're going to replace whatever we can with it, right? So in this case, we have HP. So we can create, from HP, we can create HNP. We can create not P by rewriting HN, saying, in other words, replacing the P in HP with not P by this equality, right? So rewrite HN at HP creates a new H not P. And then we also have to use exact. There's a shorter way to do this, which we'll get to in a moment, because it's a little bit redundant. But for now, oh, and also, I tried, you would think that you could do this with substitute, right? You would think that you could say something like substitute HN or substitute HP, HN, HP, something like this, right? Unfortunately, I wasn't able to get this to work, which is weird because it seems like what we're trying to do here is exactly the same as what we tried to do up here. But for whatever reason, I couldn't get that to work. But rewrite basically is usually easier to use anyways. So I would recommend you default to using rewrite when you can. Well, okay, now that we've done that, let's show the other case, right? We have, in the other case, we have, instead of having HP, we have H not P, but we use the exact same idea. And now we rewrite in the opposite direction to go from the right side of the equals to the left side to get, of course, our HP. And once we've done that, we've shown everything we need to show because we handled both cases of the classical EMP. Okay, but there's actually a much more short proof that you can do here, a much shorter proof. You can say, match both cases of our classical.emp. And in the first case, we're going to assume HP, and we get to use this weird arrow that does basically eq.rec, eq.sim, whatever, basically what we want, which is placing this in this. So that's really good for, you can type this with \t. This is exactly what we wanted to do in 2 steps in 1 step, right? This was the 2 steps, rewrite HN at HP, exact HP, right? That can be done in 1 expression with this. And then we apply that to HP because once we've rewritten HP, we get H not P. And then we apply H not P to HP to get false. And in the other case, we just go backwards, right? We get H not P. Actually, you know what's interesting? This is still doing the same idea. We're getting not P, and we're applying it to not P to get false. Next up is going to be the universal quantifier, which you already know how to prove. In Lean, the universal quantifier is super easy. It's just a function, right? This is just a function from x to whatever you have in the body of the universal quantifier. So the syntax is for all something x, for all something comma, and then your condition, your proposition. We're going to intro x here instead of underscore, and we're going to get an x as a hypothesis. And from that, we can show x equals x. In the second way, I show you how to do this with a lambda. Again, this should be very familiar to you. It's just the same exact thing as up here, but in term mode, we define a lambda x, and we apply refl from eq to x to prove reflexivity. So this way is kind of funny because we actually don't need to query at all. We can just say this is eq.refl, right? And that's what I end up doing in the second case here. But in this case, in this third case, actually, we have an interesting connection between forall and implicit arguments. Here I'm declaring x as a natural number as an implicit argument. And by the way, it doesn't matter that x is declared as nat here. It could be whatever you want. But it's an implicit argument, right? So this is just syntax for saying, let there be an x such that it's of type nat. But that's the same as saying, pretty much, that's the exact same as saying for all x of type nat, such that prove x equals x, right? So I just wanted to point out that these are all pretty much equivalent, and you need to understand that, of course, to be able to read Lean code, which uses one way or the other, right? Sometimes you'll see a lot of theorems that start with a bunch of propositions at the beginning like this, and you can translate that in your head as just, well, we know these things first, right? So we know all of them. In other words, we know for all x, and if there was a second one, we would know for all y. Sorry, we would know for all x and for all y, right? There's like an implicit. You can just like how I did with the for all and the single implicit argument. You can show that two implicit arguments is equivalent to assuming a hypothesis of those two. The conjunction, I believe, of those two, whatever the and is. So now that we've done that, let's get on to a little bit harder of a quantifier. So there exists x such that x is less than 3. Obviously, we just need to give a single example of this, 0, 1, or 2, to prove this, right? But how do we do that? Well, Lean helpfully has the exist tactic, and in MATLAB this will be the use tactic, I believe. This is going to just take an argument, and it can prove an exists by basically refining, using its constructor. This is fancy words for what we're going to do in the second case. This tactic is basically just expanding into this, where we're building an intro from the what we want to introduce, or sorry, we're building an exists from the actual thing we want to introduce and the hypothesis inside of it, right? So we're saying from these two parts, you can say that there is an x such that it does hold that x is less than 3. And that proves the goal. Now, what if we had a bit more of a general case, right? We had a hypothesis that just said that there was some x, and I forgot to introduce the x here. There is some x that is a nat, and it is less than 3. Prove that there exists an x such that x is less than 3. So we shouldn't have to be, we shouldn't need to choose a value for x to show this, right? You can imagine, like, maybe it would be harder, maybe in a more complicated example, it wouldn't be so easy to find such an x that would satisfy this equation. But if the equation matches the inside of the exist statement, we can, if the hypothesis is something that matches the existing the goals, right? We should be able to apply the hypothesis to the goal to get, true, right? So to do that, we do exist.intro xh, and we can do this because x is already declared up here. If it weren't declared, we would have to intro it ourselves. Okay, and I realize that this is kind of, if we're saying implicitly that there exists x, let there be an x of type nat, this is kind of really just actually a forall with a nested exists, but I won't get into that anymore. Okay, well, what about if we're not given a hypothesis? What about if we're just given a bare bones exist statement And we want to do it with, we want to use exist.intro instead of our tactic exists, right? How do we do that? Well, if we try to say exists.intro and then 1, we haven't finished building our exist statement, right? And what do we put here? We don't have h. We don't have anything to put here, right? Well, there are a few things you can do here in Lean when you don't have a proposition that you want, that you need. One of the approaches is to put a question mark underscore, and in, whoops, we're not in tactic mode. In tactic mode, you can use the refine tactic that will introduce as auxiliary subgoals whatever you're missing, right? So in this case, we're missing the hypothesis x is less than 3. So we need to prove that now as our subgoal. So we have to show that 1, the x that we chose, is less than 3. You can almost do that with REFL. It's not for less thans, it's for equality. How do we get Lean to actually compute that 1 is less than 3? Well, there's a few ways to do that. One is to use a simp tactic, but I recommend you stay away from the simp tactic until you get more experienced in Lean, because it will do too much for you and you won't actually learn enough about what you're actually proving. To do this, we can always use our best friend exact, right? Exact knows how to do it with a very specific lemma called whatever this is, right? But I don't think we actually need to do that. I think we can prove this a little bit easier. We can say, oh, maybe we do need to, okay. We don't need to solve problems that are already solved. I do want to illustrate though that instead of using refine, we can use the apply tactic, which will do the same thing automatically, and you don't have to fill in the holes, right? Additionally, you can use exact. So let's do another one. You can actually also use exact here, even though you don't have everything, by doing the proof inside like the parentheses, by to enter tactic mode. And then we could do something like, this, right? So now we're directly giving the proof to the proof. We're giving the proof to the sub goal, the lemma. We're giving a lemma to another lemma to show the goal. So what about not for all, right? Not for all is the same as saying that it's not true that for everything something applies, right? And to show that, the easiest way to show that is usually to show a counterexample. So to prove something like this, that's not the case that for all x is less than 3. We're going to use this not for all, which is in classical, and it's going to convert not for all into there exists not p of x. So not for all x such that p of x, if and only if there exists x such that not p of x. So once we do that, the goal changes to showing that there exists x such that not x is less than 3. Well, we can do that pretty simply by using something that is not less than 3. And 3 is actually also not less than 3. So we're going to say exists intro 3, and I'm using refine here, but again, it's the same thing as saying apply exists intro 3. You usually want to use refine if you are really struggling to fill in type holes, because it's a more loose version of apply. So try refine first, and then try apply, then try exact, right, in that order. After we refine the goal a bit, we get to not 3 less than 3. And now this is finally where we see one of the problems with Lean syntax, right? Lean has a weird syntax order precedent between not and the equality operators like less than, EQ, all of those. So in this expression, this is actually saying that not 3 less than 3 in parentheses. There's an implied parentheses, but it might be a bit more obvious here because 3 is a number, so how could you have not a number? But if these were propositions, it would look very strange because it would be saying not p equals q would actually mean not in parentheses p equals q. So that being said, you would have to put parentheses around the left side to get it to show what it looks like is showing. And that can mess you up because, when we're trying to prove this, you might think that you need to show not p, maybe EQ, whatever. You might need to show not p, or that you have not p, but really you don't. So let's continue with our proof. When we're here, clearly Lean should be able to do this pretty easily, and it can. You don't even need to do this step, but this is how you would rewrite the not LT into just EQ greater than or equal, right? Because you can convert LT and greater than or equal back and forth. And after we do that, we have 3 is less than or equal to 3. And we can use the trivial tactic, which tries, like contradiction, REFL, a few trivial tactics, simple tactics to close the goal. So here I think we could also use contradiction. Let's see if that's actually, oh, interesting. Well, trivial works. Now, at the end, I wanted to do a little bit extra here about the last unit's classical logic. The book had this answer for whatever this proposition is. And I wanted to show like my way of doing it just because I felt like this was kind of, I don't know, this seems like they're trying to use a lot of like existing functions, which they don't really need to be. This seems harder for me to understand than a more just straightforward proof, right? So I want to show you how I would do this. So I would say, well, first of all, we have a function in our hypothesis. So we're going to intro h not and, to get that not and. Now we have to show P and Q. Now maybe I actually already proved this because this looks really familiar. We had the not and, something similar to this, right? So, okay, so how do we show P implies Q from that? Well, we can intro P again, right? Because we have P, and now we just need to show Q. So how do we show P and not Q to give to HN and, right? Well, probably going to use classical.em here. Oh yeah, this is actually a really good example of when to use by contradiction, right? Because we have a goal of Q and we need P and not Q. So this is a perfect example of using by contradiction. It's exact by contradiction. Lambda not Q goes to, then we need to apply the HN, HB, and HNQ to close the goal. Okay, so now I realize that this might come off as a little bit show-offy. I wasn't expecting to finish it that fast, but this is, a good example of where you don't really need all these, like elim is mapping both sides of the OR to single, like, I don't know, this just seems a little bit absurd to me, no pun intended. Had we not used by contradiction, we could have done this a little bit differently by doing, of course, our old friend classical.em. We already have classical open, so I'm just going to say em. And we're going to give it the Q because we have P and Q. Can we show this? This is much harder with em. I don't think I'm going to bother trying to show that. We've already finished classical, so.